Hello, my name is Mark Smith, and welcome to our series on getting started with inductive position sensors. This is video number 5, where we talk about the debug button and how to use it to validate your sensor's performance. To help us with our experiments today, I got 3 evaluation boards and sensors on my bench today. I have a linear sensor, and I have a rotary sensor that you can buy from Microchip Direct, and then I have a another rotary sensor that you can download right from our website. So the linear sensor is an LXE330AL002, and the rotary sensor is an LXE330AR001. And this one's slightly different. The only difference that this one has on my bench is that it has a micro bus, and this will be available on our web shortly. And of course, I have my LXM 9518 programmer that I'm going to be plugging into my sensors. And then this one is a 30 millimeter rotary sensor that actually has a huge air gap, about close to 10 millimeters here, about 8 millimeters here. It's a really high performance sensor that can use for really good air gap ranges. Okay, and we're going to use all these to validate and go through this debug tab. So with that, let's go ahead and get over and started with the linear board. Okay, I have the linear board plugged in now, and let's go to the settings tab. In the settings tab, you'll notice our block diagram. And inside the block diagram, there's 2 blocks called the oscillator block and the AFE block, which stands for the analog front end block, that are used, and we're going to be using and digging into those signals that are inside there, and looking at the signals before they go to the MCU, the signals that the MCU reads. And we're going to look at using those signals to help us to validate the sensor's performance. So if I go over to the measurement tab now, I got the debug button up, and over on the right is a detailed block diagram of what's going on in each of those blocks. I have an oscillator, and then I have our AFE block. So let's go through these signals. I got the oscillator is generating our magnetic field. And then I have 2 receive coils, CL1 and CL2, that are receiving the signals, and they go through a demodulator. They go through an ADC, and then we get what's called raw sine and raw cosine signals. So a lot of these signals do not correlate to the debug tab. Raw sine is shown here. It's a 13-bit unsigned value. Raw cosine is shown right here, another 13-bit unsigned. And then you see an oscillator voltage, and that is actually shown here. We can read the oscillator voltage through this debug tab. There's the output parameters. And then we have a value called radius. Now, radius is the control law that our AGC, our automatic gain control, uses to maintain a constant amplitude of our sine and cosine. It uses a trigonometric identity called sine squared plus cosine squared equals to a constant, and that's a trigonometric identity, and that is our control law here, and its job is to adjust the oscillator voltage to ensure that the sine and cosine signals are the amplitude's the same, or sine squared plus cosine squared equals a constant. And you can see as I adjust this the air gap right now, you can see I can adjust the air gap going to like a maximum air gap, and of course the oscillator increases. And then I drop that air gap down, the oscillator voltage drops. Now the other cool thing is, if you notice, as I go up and down here, the radius will stay relatively constant. And if I didn't move my finger, the output will also be constant too. So that's the idea, is that over air gap, both the output and the radius stay relatively constant. And I'm just doing this with my hand. So, and then if I go too far, I will get a fault condition, or I go too low. If I drop the signal too low, have the signal be too large in value, I can get what's called an oscillator undervoltage. UV stands for undervoltage. And this one's an oscillator overvoltage error. Now there's other errors that can occur, and they will show up in this debug tab. And the importance of this debug, this error indicator block, and it's important that while you go over your measurement range and you're looking at the maximum air gap or minimum air gap of your sensor, you want to ensure that there's no faults that are occurring over here. So far, we've been looking at the signals as they show up on the debug area in these graph here. But as we capture the data, when we capture the data, all that stuff gets stored in this capture domain. And that's one of the reasons why, in this capture signal, that's one of the reasons why we recommend that when you capture when you do your sensors evaluation and measurement, you actually use the Debug tab because all those signals get captured. So let's kind of go through that real quick. ADC1 is the raw cosine value. ADC2 is your raw sine value, and these are 13-bit unsigned signals. And then ADC3 is our oscillator value. Then there's what's called a theta value. It's our raw angle measurement. Then there's a post-linear, that's after our calibration phase. And then we do what's called an adjusted ADC1 and an adjusted ADC2, which is really just this value minus 4095, or getting rid of kind of the offset that's in the system, and subtracting 4095 and then inverting it. I believe that's an inversion here. So ADC1 is the adjusted value or signed value, the signed cosine and sine value. And then there's a fault. If it's 0, there's no faults going on. Then there's an analog voltage because we're reading IO3, and then a digital value of that analog voltage. So those are all the signals that are needed for your debug that are all kind of represented by these graphs over here. And so that's how you use it to validate your sensor's performance. So let's jump back over to our rotary sensor and look at its performance over its measurement range. Okay, I have the rotary sensor hooked up now, and you can see that I got the debug tab working, and I have a pretty good air gap. It's pretty well fixed over that measurement range, but you can see that the oscillator stays relatively constant, meaning the air gap's not moving around. Now I can move the air gap. I can go up and down a little bit. You can see that, but you can see the output's not changing very much. I can just pull it up. But let's see, as I move this over the measurement range, what I want to ensure is that both the radius, now the output's changing, but really make sure that there's no faults. And this one, the air gap is quite close, and so I have good performance here. And so that's just a good example, and this is a high performance sensor that has very linear and very good. Now let's look at it using kind of one of our this sensor that you can download from the web. Okay. So I've gone ahead and connected the LXM9518 to this Make It Easy rotary sensor, and I've created a really large air gap. In fact, too large, I think, for this sensor. We'll see about it. You can see how large it is, close to maybe 15 millimeters. And I go ahead and I show you can see the oscillator is quite high in this particular angle, but what I want to do is verify it works over all the angles. So if I do over all the angles that I need to operate under. And so in this case, if I'm going around and sure enough, I see a problem around degrees 80, I get an oscillator over voltage fault. And then there's a DAC output, an IO3, which is showing that. And you can actually see that the DAC is showing a fault indicator. Now in debug mode, the sent channel, which is sending the debug information, won't go into fault mode because it's sending all this information down the channel. But the DAC will go into a fault mode where it shows it's at 0. And sure enough, I go around and I actually get another signal, low signal, because the radius is actually too low here. And I can go around and then it comes out of fault mode. If you're in a development phase and you want to actually just turn off the fault mode for the DAC output, you want to go ahead and because you're just in the development phase and you just want to shut off that fault mode, there is a way to turn off those faults, and you can do that by hitting safety mode off, and you hit the program mode, and now into those same conditions that you would get a fault, you're still indicating a fault here in debug mode, the DAC is actually still outputting data. So it's a way for you to still get some signals out of, some position signals out, even though it's not as good a signal. The radius is low, your oscillator voltage is quite high, you're not getting as good signal strength. These are all things. So that's a way of kind of, pushing the limits, so to speak, of your sensor design. So with that, the other one I wanted to show is that let's go ahead and fix this. I will by dropping the air gap. Okay, so I fixed the air gap here, and you can see that now the air gap has a good air voltage right in the middle. The amplitude is quite good, and then what's important is as I go 360 degrees, I'm not getting any fault indicators, and the output voltage is going up. I hope you enjoyed this discussion about all about the debug button and the signals coming across and how you can use that to validate your sensor design. Thank you for listening, and I hope to see you in the next video.